Weird. Hello to you in the room too, but hello to whoever's watching online. I'm David. I'm the coordinator of the Maths Learning Centre, and it's semester 1 2019, and that's enough of my face. We're doing a revision seminar for Maths 1M, and there were several requests that I've been given, and I will do my best to cover what I can, but I make no promises. The rules are that feel free to interrupt me. There's a limit to how much interruption I can cope with, but feel free to interrupt me and ask me questions, tell me that I've done some of my working wrong. I'm notorious for leaving minus signs out and doing 1 + 1 = 1. So just feel free to interrupt me, ask me how I made decisions to do things, but at least wait till I finish a sentence usually if you want to interrupt me. And at any point it is okay to ask questions. This is for you, not for me. I don't need to do this. So if you have any questions about what I'm doing before I move on, then please ask. Okay, cool. So the first thing I'm going to talk about is related rates. You guys listening online, you had to ignore all of that because you can't ask me questions because you're watching from the future. The people who are here are lucky they can ask questions. But if you're listening online, you can always drop into the Maths Learning Centre and ask me something. Okay, so, right. Well, my understanding of the related rates bit of this course is that you have some problem where things are changing and you're asked what the rate of change of something is at a particular moment, something like that. Goes to know rate of change, which is often a speed. At some moment. That's what I'm thinking it's about. Good. I have to write everything down so that when the handout goes out, and if you just want to download just the handout, you can have a sense of what's happening. So I have a question. What is it that makes these sorts of problems hard? Yep.
Oh, it's just like recognizing what the different parts of the problem actually represent when they're split into like the one in the course notes was like about an oil slick expanding.
Mm-hmm. Okay, I'm hoping that I've heard this right, what the different bits represent and how they're related. Okay. Oh, is it? Okay. Okay, so we want to make sure we're talking about how to decide that from the text of the written problem. I'd really be cool if I could look at the one that was in the notes. Does anyone have that? There's a man who knows how to use a binding machine.
Was it in vectors?
Yeah, weirdly. Well, none of the related rates problems use vectors, so it was just weird that it's there in vectors. I think I can get it. Thank you. Okay, so these are the outline notes for Maths 1M. If I was doing this properly, I should do a proper reference and tell you who the author is, but it doesn't say, so we're assuming they're written by someone in the School of Math, you know. So this one here, the oil slick. All right, let's do that one. And if I'm very clever, I can have both my writing and that on the screen at the same time. Okay, do you mind if I draw on this? So, well, let's just do a problem. 4.4.6 from page 144 of the Maths 1M notes. Okay. So we'll do it and then we'll go back and see what I did so that we can have an idea of how I did what I just did. So a circular, I'm just going to read the whole thing. A circular oil slick is expanding on the surface of the ocean. When its radius is 200 metres, it's expanding by 0.1 metres per minute, and the thickness is 0.1 metres. At that moment, how fast is the area of the slick expanding? If the thickness is the same everywhere and the volume of the oil is fixed, then how fast is the thickness decreasing? Okay. There's a lot going on there. So the first thing I'm going to do is ignore all the numbers and try and have an idea of what's happening. So, well, it's a circle. And there's the ocean. Beautiful. So at a particular moment, the radius is 200 metres and it's expanding at 0.1 metres per second. Okay? Minute. I'm so used to being in physics where you don't do things like metres per minute. And at that moment, the thickness is 0.01 metres. Okay, so it's actually like, I shall model it by a teeny tiny thickness of cylinder, maybe. I don't know, I'm not sure, but I'm just trying to make sense of everything that's going on here. I probably should have ignored all those numbers. It's not really important what those numbers are at the moment, but it has a certain radius, it's expanding at a certain speed, and it's got a certain thickness. At that moment, how fast is the area of the slick expanding? Okay, so the eye just thinking just from above, we've got a circle and it's getting bigger and bigger and bigger, right? Okay, cool. Just thinking about what's changing and what's staying the same. This is the 200 metres here, and it came from a little bit less than that and it's going to a little bit more than that. Okay, cool, good. So we want... That's something that they've mentioned. And if the thickness is the same everywhere and the volume of oil is fixed, how fast is the thickness decreasing? Okay, so thickness. Volume is fixed, so that's a goal there. And we want rate of thickness. Okay. Right, there's a lot happening here. So just based on the order that these are in, I'm assuming that you can figure out how quickly the area is changing without knowing anything about the thickness, according to the way this question is written, because the mention of the volume and the thickness didn't come until after that. Okay. So let's see. So I'm going to have to make... Okay, so the quantities that are mentioned so far is the thickness and the volume and the area and the radius. So those are the quantities that are mentioned in this problem, thickness, volume, area, radius, and we have various rates of change of those things. And so technically there's time involved as well. So they're all the quantities involved. So it would be reasonable to try and figure out some formulas that connect those things together. They seem to be everything that's involved here. So I reckon I should give them all letters. So let's call this R, this A, this V, this T. Oh, no, I can't call it T. D, for depth, and this would be t for time. Okay. I choose my variables. Okay. So, rates of change are derivatives. And so I need to know how these things are related to each other before I can know the derivatives. So how is radius related to area? I can do that for a circle. That's definitely true. And how is volume related to any of that? Okay, so volume would be the area times the depth if it's a cylinder, which would be the same as this if I really wanted, because that's what the A is. And that seems like everything that I could figure out. Just a second. Why won't it open? How bizarre.
Wait, what about variables also like speed, right?
Well, what I'm doing is that anything, I'm doing variables that have, yes, there are things which are speed, but I can write the speed in terms of these things. So you're right, there is also speed of the rate of change of the radius and the rate of change of the area and the rate of change of the thickness and the rate of change of the volume. They're all there too. So it's a worthy point. But I deliberately didn't use them because I'm assuming they're going to come out when I do the derivatives. So I might just put a note there. So I didn't include speed because it's a derivative of these. Okay. But there's nothing wrong with you putting speed in as well, if you want. Okay. So it seems to me that I could do derivatives now and see how the derivatives of everything is related to the derivatives of everything else, to see if that helps. So let's see. Formulas, derivatives. Okay, so if I differentiate this one, then I'd get dA on dt and do derivatives with time because I want speeds, I want rates of change. Pi is a constant multiplied on, so it will still be there. The derivative of r squared would be 2r, but because of the chain rule, I'll have to do dr on dt. Because I'm imagining that everything is a function of time, so there's a function inside here, which is what r is, that I have to differentiate to get this bit here. Okay. Cool. And what else have we got? We've got v is a d, so I could do dv is, product rule. So this would be differentiate the a and keep the d, and then keep the a and differentiate the, oh damn it, oh well, we have dd on dt, we're going to have to lump it. Shouldn't have chosen a small d for that. Oh well, it's stuck now. I could go back and change it. What was that? Okay, cool. So these are all my derivatives. I could have done this derivative directly on this one as well, but it seems to me that if we have already figured out what dA on dt is, we should be able to sub it in there. Okay. So now let's figure some stuff out. So when r equals 200 meters, dr on dt is 0.1 meters per minute. And so from that information, we could say that dA on dt would be pi times 2 times 200 times 0.1. Because all of these things go in this formula here. Which would be whatever it is. 400 times, whatever pi times 40 is. 120-ish. Need a machine to do that for me. Really must bring actual calculators to these things. This would be in meters squared per minute, I guess, because it's a rate of change of area. And this one was in meters and this one was in meters per minute, so we'll get meters times meters divided by minutes. Okay, to one decimal place. All right, and then what else did we have to know? What the rate of change of the thickness was? Okay, so also, what are we going to get? We're going to get dV on dt well, the only formula that has the rate of change of thickness in it is this one. So we want to figure that out. So we need to use that formula. When r is 200, dA on dt we just figured out was 40 times pi, and A is pi times r squared, which is pi times 200 squared, and dV on dt is 0 because the volume isn't changing, since the volume is fixed. And so we get, from equation number 2, because I've just labelled it, we get 0 equals dA on dt, which was 40 pi, times the thickness. And what's the thickness currently? 0.01? Yep, there it is. Plus the area, which is 200 squared pi times d on dt. Cool, so I can rearrange that to figure out what dd on dt is. Okay. So dd on dt would be this divided by this, whatever that is. The pi's cancel, that's kind of nice. 200 squared would be 400, 100. I reckon I can do that one without a calculator, actually. So that'll be a 1. Get rid of that. One, two, three. Right. So we had 0.01 and we had to divide by 1,000, yep. And so this would be in meters per minute. Yep. EQN for equation and 2 for 2, because I labelled it when I got there, so that when the person marking my exam reads it, they know what I meant. Or me in the future. This one, because I thought I was going to label this one, I should label the other one too. So back here I'm actually going to go equation 1, there. Okay. Well, there we go. It makes sense that if... It seems to make sense to me that the thickness wouldn't be changing particularly fast, because it's pretty small already. So, Yeah. Okay, so what was it that I did to make sense of this problem? Sorry? Yeah, I drew a diagram. It's always a good idea to draw a picture if you can. Sorry? I did find what's given, but if you notice very carefully, I didn't use any of those numbers until later. I found the variables that were given. I had to find which things were changing, like what numbers were being described, but I didn't use what the values of those were until much later. So let's see if we can do another one, and I'm going to get one off the internet this time. I'll just leave that there for a second. Yep.
There was this question. I think it's probably like the best one to know because it's like the ladder.
Okay. I'll see if I can get one that's similar because I don't want to get one out of your actual assessment. That sort of thing. This one's in feet. A 50-foot ladder is placed against a large building. The base of the ladder is resting on an oil spill and it slips at a rate of 3 foot per minute. Find the rate of change of the height of the top of the ladder above the ground at the instant when the base of the ladder is 30 feet from the base of the building. That sort of thing? Okay. Let's do it in feet because that's fun. You can tell that that must be from an American website. So I just googled related weight relates practice problems, and this is the first thing that came up. Okay. So I'll take this away, but I may need that again. So if I forget to give it to you, I'll take it to the Maths Learning Centre. So this one's from Illinois Uni. It's probably the University of Illinois, but that's close enough. Okay, so we have a 50-foot ladder. Is against a large building. Base at a rate of 3 feet per minute, which is the worst speed of all speed unit. Though if you ask Google to give you a rate, the conversion of speed units, it gives you it in beard seconds as well as a unit of speed, like how quickly beard hairs grow. So find the rate of change of the height of the top of ladder. Ladder top above the ground. At the instant when is 30 feet from the wall. Okay, I had to write it all down because I don't have it on page. Okay. So the first thing I'm going to do is try and understand what the situation is, and it's a classic. I should probably slow down my writing so it's easier to read. That's why I'm so good at teaching medical students. It's a very old joke. Okay, so there's a building and there's a wall, there's a ground and there's a ladder. That's my building, that's the ground, and this is my ladder. And it's sliding this way. Okay, so that's the story, and presumably as it slides this way, the top will slide down this way. It would have to do that pretty slowly, actually, in order for the top of the ladder to maintain contact with the wall. Like if it slipped outwards really fast, it would leave the wall. So, but anyway, it's a maths problem, not a physics problem, so we'll just presume that the top of the ladder goes down like that. Okay, so that's the situation as far as I can see it. And the ladder is 50 feet long. Which is about 16-ish meters. No. Yeah, that's right. Okay. All right. And cool. So it seems to me that everything, the one thing here isn't changing, which is how long the ladder is. That doesn't change. So what I start doing after I've got the situation is what's changing and what's staying the same. So the ladder stays, the length of the ladder is the same. Stays the same. What is moving? This is changing here. The position, how far this is from the bottom changes. Distance of bottom from the building changes. And the distance of top from the ground, that changes too. I think that's all the quantities that are going on here, other than time, obviously. There's always time. Okay. So they're the physical quantities that are changing, and presumably there's also the quantity of the speed at which both of those things are happening, but I'm not going to include those because they change when time changes. Yes?
So you're basically listing what is happening.
Yep. Yep. What's happening in the situation and which things are staying the same, which things are changing. Okay. So the things that are changing are going to need variables because they're not always the same, and so they have multiple different answers, so they need letters to represent them. And so we shall call this one, well, let's call this x and this y because that sounds nice to me. So let x be distance in feet from the building, and y is the distance in feet of the top from the ground. And they're the only two things in my story that were changing. In the previous story, the things that were changing were the radius and the area and the volume and the thickness. And so I gave them all letters. So in this one, the two things that are changing are these. Okay. And so now I want a formula that connects the information I have together as best as possible. And I see a triangle here, and so I reckon Pythagoras' theorem will provide the formula that I want. Okay, cool. Now, I haven't even written down the other information we've got here. I haven't got any of the numbers about the speeds. It says that the base is slipping at 3 feet per minute. Okay, so we're at 3 feet per minute is the rate of change of the x, and they're asking us what is the rate of change of the height, so that's the rate of change of the y, that's the goal there. So I'm going to have to differentiate this to get a rate of change. Derivative with respect to time. So let's see. If all of these are functions of time, the derivative of this would be 2x, but because of the chain rule I'll have to do dx on dt. And the derivative of this with respect to time would be 2y, but because of the chain rule I'll have to do dy on dt. And this is a constant, so its derivative is 0. Everything's got a 2 in it, so I'll just divide by that because that's nice. Okay, so my goal is to figure out this one, that's the goal there. And so I'm going to need to know what all of these other things are. So what have we got? We've got x is 30 feet, according to the problem. At the moment, that's how far that is. We've got dx on dt is 3 feet per minute, according to this. We're going to need to know what y is if we want to know what dy and dt is. So we're going to have to find y. So let's see. X squared plus y squared is 50 squared. So y would be the square root of 50 squared minus x squared, which is whatever that is. Which is 40. Aha! Look at them making it easy for us. Because it's a 3, 4, 5 triangle. And so we've got, so now we can sub in 30 times 3 plus 40 times dy on dt is 0. I'm only mildly distressed. Oh no, yep, that's okay, it's all good. So we've got 40 times dy and dt is minus whatever 3 times 30 is, and so dy and dt so that would be 90 divided by 40, which is 9 divided by 4, which would be 4 1/2, 2 1/4. And it should be negative, because if the top is going out, the bottom's going out, the top should be going down, so we're doing well. At 2.25 feet per minute. Okay. So it's not like, I mean, to be honest, it's not like this is a method per se. It's just a useful way of attacking any problem. But a useful way of attacking any problem is to try and figure out what the situation is before you think about what the numbers are doing. But in this problem, because the numbers are moving, the numbers are changing at, you know that it's 30 feet at the moment, but that's just 30 feet right now. A second ago it was a little less than that, and a second from now it'll be a little more than that. So anything that's moving is going to need a letter to represent all of the numbers it could be. And then all the other things come out from the derivatives. How are you feeling? All right. So the ladder is classic. It's classic. So if you in the future study a course called Dynamics, it's full of these problems. One of the reasons they have included related rates in Maths 1M is so that people who study dynamics in second semester are better off. If you're not studying dynamics, then well done to you. But this is the sort of thinking you're going to have to do at the very beginning of dynamics and all the way through the entire course, if you do it. Sorry? It is a physics course for engineering. It is the and it should be somewhere in Physics 1 if you're doing physics. But yeah, the physics course engineering has 2 physics courses: statics, which is the physics of things that don't move, and dynamics, which is the physics of things that do move. Okay. Paradoxically, the textbook for dynamics has a bridge on it. Okay. I think I'm okay. How are people feeling about moving on from related rates now? Okay. Okay. So of the things that are here, we have some things about complex numbers, we have differential equations, we have some things with parametric curves. Does anyone have a particular preference of what I would like to talk about next? Is there a consensus? So if I was going to choose complex number things or parametric curve things, if you would prefer complex numbers, could you pop your hand up? If you would prefer curves, pop your hand up. We'll do that first. Okay. Now, as relaxed as we are, I am going to need people to not talk because I can't concentrate if you're talking too loud. Okay. All right. I mean, we could call it parametric curves, or we could just call it like curves because it doesn't really, the parametric doesn't really matter. So a curve to a mathematician is essentially something that you could draw by tracing a pencil through on a page or through the air. It doesn't have to happen. It can be in 2D or 3D. Yeah, your lecturer only did them in 2D, right? Okay, right. So the idea is, if you have a curve, then there is a variable which tells you where you are on the curve. If you were paying attention when I was drawing it, you could capture a video of that, and at every second you could locate which point my pencil tip was at every second. And so there is a variable in my video that says, given the time, what point I'm at. And that's the idea of a parametric curve, that there is a variable, it doesn't have to be time, but there is a variable that tells you, given the value of that variable, it tells you which point of the curve you are at. So it's traditionally t for time. And in my head, t lives on some sort of axis, like it's just on a number line, and as t moves, so you move along the curve. And it might be that you're moving faster at some places than others. So it might be that when you're here, it's going pretty slowly along the curve, and then it goes really quick. So I'm trying to make this, do my two fingers do separate things. If this is supposed to go along at the same speed, it might go at different speeds in different places. That's important. So it may be that when t is 0, we're here, and here when t is a half, we're here, and it may be that when t is equal to 3/4, we're here, and then finally when t is equal to 1, we end up at the end. And each point here produces a point there. That's how a mathematician thinks about a curve. And there might be more than one way of describing a curve using a number like this, which is called a parameter. Okay, which is why we call them parametric curves. So, I know it's a curve because it only has one parameter. If I needed two parameters to tell me where I was on the object, it would be a surface. Like the surface of a ball needs two numbers to tell you where you are. Just like you do in a plane, you need two numbers. So, yeah, a curve needs one parameter to tell you where you are. Cool. And I can figure out various things. I mean, the main thing I want to know is be able to locate every point on the curve. This curve loops over itself, and so it has some of these points will be located twice. I think it might happen once when t is like a quarter, and then again when t is 0.6. So it would be nice if it only happened once each, but a curve that loops around itself, it's really difficult to do that. So the first thing is to have a formula which tells you what every point is based on the value of t. And the second thing is to think about how quickly a point is moving as the t moves, and which is why we have related rates nearby to this, because there is a related rate here, which is how quickly the x coordinate's changing and how quickly the y coordinate's changing if you are constrained to be on the curve. All right. So ideas that we need. With t, find the point, but also find like the speed. You might also want to know what direction the curve is pointing at any given moment, and that's a tangent. So just to see, if I was at this point here, then as I move around here, it's sort of going that way, and that's the tangent there, whereas this one is going that way. So you're interested in the direction that it's pointing as you move past this point. Okay, oh, wow, okay. Right. No, the reason I'm talking like this is I'm sorting in my head what I want to say. I don't have the advantage of your lecturer of being able to prepare for this. Okay. So let me just give you an example of some classic curves. There's a really cool classic curve which is a circle. These are the ones where you go, yes, I remember that one. It was episode 3. It's a really good joke. Classic. So a circle is one of your classic curves, and it's one of the ones that you should remember for the rest of time, how you create it from a parameter. And it goes like this. That is very not central. I would not pass the interview to paint the Sistine Chapel. Okay, so with a circle, you can locate every point on this circle using the angle that you've rotated. So if this radius is r, then this point here will be r cos theta, r sine theta, where theta is the angle that you've rotated. And the theta will go between 0 and 2 pi, and it will cover the entire circle. Technically, it will cover the beginning and the end twice. This is a classic parametric curve. And a lot of times when you write parametric curves, you will write them as, x equals r cos theta and y equals r sine theta. So that's a classic. And most parameterizations, they're called, if you want to find a way of describing a 3D object, a really useful way of doing it is to cut it into circles and use this. And the students in multivariable calculus 2 are currently needing to know how to do that. But also happens in physics. Okay, so that's your circle. You can adjust this just a little if you want, and you can move your circle to a different center. and you can do all these fun things. So I'm just going to do one of them. Centre like AB. So here's AB, and here's my circle, like that. So here's the thing. I know that if this was centred at the origin, it would be r cos theta, r sin theta. And I know that I'm just starting at A and then going the vector r cos theta, r sin theta. And so you're actually going to get the points on the curve, x, y, equals A plus r cos theta and B plus r sin theta. And what most people think about that is they do it in vectors. They go, there's a vector that gets you here, which is the vector AB, and then there's a vector that gets you here, which is the vector r cos theta, r sin theta. I don't know if this is important, I just wanted to show you how you could do some of these things. Just in case, if you've seen it, then that means that when you see it again, it won't be so bad. And the other thing is, I think is cool, is an ellipse. I love ellipses. An ellipse has two radiuses. It has a radius in the x direction and a different radius in the y direction. And it is r cos theta and s sin theta. So basically the same as a circle, except you use the x radius for the x and the y radius for the y. It's very nice. Cool. And the only other classic curves that there are two others that you know already and you didn't realise you knew, and one was a straight line. So if you have a straight line between 2 points and it joins point AB to point CD, that curve in inverted commas there doesn't have to be curved to be a curve from a mathematician's point of view. I can create this by thinking vector-wise. To get to this point xy, somewhere in the middle, I need to start at AB and go some percentage of the distance from here to here. So I can do the vector from here to here. So you do end minus beginning. And then xy will be start at AB and go t lots of the vector where t is between 0 and 1. Because t is the percentage of this vector that I've gone. So if I'm halfway, I'll use the t as 0.5. If I'm 75% of the way, I'll use the t equals 0.75. And that will give me the answer I want. Which means we can create a little formula for this if we want. We can simplify that a bit, but it's not really important. We can just leave it like that. So you can make the straight line between 2 points as a parametric curve by thinking of what percentage of it you've covered, the vector between them you've covered so far, which I love a lot. The only other parametric curve that you have seen that you didn't realise you had seen is basically all functions ever. If y equals f of x, here we go, right? Then the point xy is x f of x. And the parameter is x. The x coordinate tells you which point you're up to. It's a perfectly good parameter for whichever x's are actually allowed. So they're all the curves that I reckon you might have met, and then there's just random ones. Just make up a random crap. And you just stick a formula in the x and a formula in the y, both in terms of t, and there it is. And you just, and if you had a machine, like something like Desmos, you could actually type that in with the t's, and it would just draw it and show you what it looks like. But otherwise, you'll just try various different values of t and plot all the points and see what happens. Okay. All right. Cool. So let's see. That's describing points using the various things. Let's talk about finding speeds and tangents. Okay. So, right. Maybe I'll look up to see what your lecturer says about this. Oh, look, I have mentioned the ones that your lecturer mentioned. Good. Just in a different order. Okay. Cool. So I may think differently about this than the way you've seen before. The way derivatives work, derivatives are about very small changes in things. If I change time by just a little bit, how much does the area change? That's what we were doing before. And in this question, we would think, well, if I change the parameter t by just a little bit, where does the point move to? It moves just a little bit. So this is the thing that I'm going to imagine here. So here's t, the t's, and here's the curve, and this point here is producing this point here. If I move this by just a teensy bit, a little tiny change in t, then this will move by just a little bit. But that thing will be created by a change in x and a change in y simultaneously. So I'm just going to zoom into this. This is my magnifying glass. That's made of a change in x and a change in y. Okay. Nice color coding. And if I zoom in far enough, then my curve will look flat. Almost completely flat. That's the whole idea of derivatives. If you're extremely close to the curve feels flat to an object that lives on the curve. And so, and that's the tangent. It's the line that this curve is trying to be when you're very close to it. So the thing is that the x changes by a bit in response to the t, and the y changes by a bit in response to the t, and this vector is the dx and the dy. So when I think about speeds and tangents, I think that I can actually have the point which has a function of t here in the x and a different function of t here in the y. I can actually think about that and just differentiate them both. I differentiate them both, and this vector is that there. Just a little vector there, because I really want to do it relative to the dt, because the dt is really small. So, if I want to draw the tangent, then the tangent will be this point plus some parameter times this vector, because that's how you make lines from a point and a vector. So it's really cool. I love it. But even better, if I want to know the slope of this, it will be dy divided by dx, which will be dy on dt divided by dx on dt. Because these dx's and dt's and dy's, while they don't really exist, they're very small numbers. They behave like numbers if we squint. Yep?
Well, how do you suppose the x has a different or y has a different parameter? You've got like two parameters?
These both have the same parameter, but there's different function in each one. So this might be like cos t, and this one's... No, they're always the same parameter if it's a curve. If there were two parameters, this would be a surface and not a curve. Cool. So, yeah, but this is more like, this is cos and this one's sine, but they've both got a t in them. That's a good question. Okay, so the slope of this vector is the slope of the curve at the moment, which is the same as the slope of the tangent at the moment. Sweet! So what does that mean? That means if I want to find the slope of the curve and the rate of change of x and the rate of change of y at any given moment, I just do derivatives. So it's probably best to do it as an example. All right, let's do this curve. I have not the slightest clue what this curve looks like. I just want to give it a go. Okay, it's going to be fun. So this is my curve, and I am going to try and figure out what the curve is doing at the point where t is pi on 2. Okay. So I can find the point that it is. It's that, whatever that is. 3 to the pi on 2, I would need a calculator for. It's only going to be 4 and a bit. Nope, 5.6. And I know that sine of pi on 2 is 1. Okay, so that's where it is. It's at the point 5.621. If I go a little bit to, if I go my t just a tiny bit back, the sine will be smaller, and this will be smaller. So it'll be heading sort of down that way. So I'm just thinking about what's happening. When the angle's smaller, the sine gets smaller, and so it's going to go back a little bit in the y, down a bit in the y. And when this gets smaller, it's going to go that way. So I reckon it's coming past like that. I'm just imagining what happens when I make that smaller or bigger. But I'll be able to confirm that in a minute. I have no idea what the rest of the curve is doing, but I know it's going through this point and it's sort of coming past in a generally upwards direction. Okay. So I can do the slope here, the rates of change. Dx on dt, well, x was 3 to the power of t. And so dx on dt, damn it, x was 3 to the t, dx on dt would be, now how do you differentiate 3 to the power of t That would be ln 3 times 3 to the power of t. So when you differentiate e to the t, nothing happens. When you differentiate something that's a different number to the power of t, you have to multiply by ln of that number. Okay? Which is at this point. .17-ish. Okay, when y is equal to y is sine of t, so dy on dt would be cos of t, which is, oh, interesting, 0. Well, there you go. Oh, I was right. I did not think about that clearly at all. If the t goes back a bit, the sign goes down. Oh, it goes down in both directions. If the t goes back a bit, the sign goes down, but if the t goes forward a bit, the sign also goes down. This is the top of a hill. Beautiful. Okay. Okay. So the direction that this curve is pointing at the moment is in the direction of this vector, 6.170. So the slope at this point, it'll be dy on dt, which is 0, divided by dx on dt, which was 6.17, which is 0. Well, there you go. So since the slope is 0 at this point, the tangent is going to be y equals something. The tangent equation is y equals, slope times x plus c for some c, which in our case is just... and so... it passes through 5.621, and so therefore it's y equals 1. I really should do another example where it doesn't turn out to be a slope 0. Okay, so I'll do this one, just a random curve. So this one is t squared 3t plus 5 for t between 3 and 7, and I want to find the tangent when t is 4. So when it says find the tangent, remember that the tangent is the name of a line, and you therefore need to find the equation of a line. If it says find the slope, you just need a number, but if you find the tangent, you need an equation for a line, because they're different things. I say this because I've seen people just give a number when you ask for a tangent. So dx on dt is 2t, dy on dt is 3. So at t equals 4, you get that xy is 4 squared 3 times 4 plus 5. Which is 16, 17. And dx on dt is 2 times 4, which is 8, and dy on dt is 3, and so therefore the slope at this point will be 3 on 8, because it's the change in y divided by the change in x. And so the tangent will be y equals 3/8 of x plus some constant, and you do need to choose that constant so that it passes through that point. And so we get 17 is 3/8 of 16 plus c. I went just over the page. Well, an 8th of 16 would be 2. And so the c is 11. Therefore, the tangent has equation y equals 3/8 of x plus 11. Okay. Okay. So this curve, the other curve, because the tangent was horizontal, that meant it was a turning point from above. So the curve went like this in the other one. This one, the slope is 3/8, so it's going past this point upwards. Not very fast upwards. And 3/8 is my favourite fraction, so that's kind of nice. It's my favourite fraction because it's the number of litres of milk in a block of Cadbury chocolate. Okay. Anything else about parametric curves before I move on that people have been worried about at some point? Okay? No? Oh no, there's that thing where you turn it into a Cartesian equation. I'll just talk about that just a second. So, a Cartesian equation is a different way of describing any object. So when you have a curve, we have one way of describing it, which is a t which tells you exactly which point you're up to. A Cartesian equation is a rule that if you sub in the coordinates of the point and it works, then you're on the curve, and if you sub in the coordinates of the point and it doesn't work, then you're not on the curve. That's the difference. So just as an example, if you had xy equals cos theta sine theta, which is this circle, you could just as easily have this version. So this one tells you what every point on the circle is. You choose a theta and it tells you a point on the circle. This one tells you none of the points on the circle, but it does give you a rule for telling if a point is on the circle or not. So I can say, is 0.6, 0.8 on the circle, and you would go, okay, well, 0.6 squared plus 0.8 squared is 0.36 plus 0.64, which is 1, so yes, it is. And if it came out to anything other than 1, it wouldn't be on the circle. That's what a Cartesian equation is for deciding whether something is part of the curve or not. And so the trick is to try and be able to turn one of them into the other. There's no real reason to do that, but other than people keep asking you to do it, and so you need to know how. So one of the classic ways of doing it is to use this fact that if you have cos theta and sine theta, it will give you cos squared plus sine squared equals 1, and that's a classic way of achieving the thing that you want. Otherwise, you just have to find a way of getting rid of the t. So Find a Cartesian equation for the curve xy equals, what was the one that we had earlier? T squared 3t plus 5. Okay. So the goal is to have something that is a rule that if you sub in the x and the y and it works, then it's part of the curve. And so what we're going to do is we're going to start with this. And we're going to try and think of the simplest way we can to get rid of the t's and form a single equation involving x and or y. I like to avoid using square roots if I can, because I don't know if it's the positive or the negative square root, but I can totally rearrange this to get t equals and then sub it in there. That's one of the classic ways. So from 2 I can get 1 minus 5 is 3t, 1/3 of y minus 5 is t, and I can sub into number 1, so x is that. And now I have a perfectly good equation. Maybe this one feels nicer. I like this version. I could have stopped there. That's a perfectly good Cartesian equation. But this one just feels prettier. So I went there. So this is saying that if I just had a random point and I wanted to know whether it was part of this curve, then I could sub it into here, and if it worked, then yes, it's part of the curve. And the other one is where you see something like something like that, 3 cos t, 5 sin t to the 7. Now, I do not like my chances of reasonably getting t equals and subbing it into the other one. Because at the very, I'd get x on 3 and cos inverse, and then I'd have to sub cos inverse into sine, and that's just extremely unsatisfying, especially because I don't know, because cos inverse only produces some of the possible values of what could have gone in, and so that's not going to be helpful. And so it's a trick, really. I know that cos squared plus sine squared is 1, and I can figure out what cos and sine are from this and sub it into that, and that will get rid of my t's. So from number 1, I've got x on 3 is cos t. And from number 2, I've got y on 5 is sin t to the 7. So y on 5 to the power of a 7th is what sin t is. And I know that cos t squared plus sin t squared is 1. And so therefore I can sub that in. And the t's are magically gone. Done. If a person writing an exam question was being particularly bloody-minded, they may use, sec and tan. And you have to use that trig identity instead. Okay. This thing looks very like the equation of a circle, and it is. It'll probably just be kinky at the corners. People tend to call this sort of thing a squircle. Though, no, this one's probably going to sorry. a squircle is x to the 4 plus y to the 4 equals 1, because it looks like a square with rounded edges, rounded corners. This one's going to tend to point outwards because the powers are less than 1. So I really want to see what this looks like. Just a second. You couldn't do this in an exam, but what was it? Y on 5? There it is. If this 2 had been a 2 on 7 as well, it would have looked like that. Anyway, there you go. Right, that's enough of parametric curves. Now, there were at least some people who put up their hands saying, please talk about complex number things, so I will do that too. We have about half an hour to go, and I will go over if I need to. So I've specifically been asked to talk about complex equations. So that's mean like finding a graph of the solutions of like a complex equation, that sort of thing. Okay, complex zeros of polynomials and de Moivre's theorem. Okay. Well, here we go. There is a couple of revision seminars on complex numbers on the web page already. Right, we're ready. There's a couple of revision seminars on complex numbers already where I go through all the different operations of multiplication, division, powers that you can do with complex numbers. So I'm not going to go through all of that. I'm going to specifically talk about these things, if that's okay. But I will say complex numbers are very cool. They were originally invented to solve cubic equations, and only later we discovered that they solve quadratic equations. And it wasn't until much later that we realized that they were able to describe transformations in the plane. So that's the really cool thing. So there's always these 3 ideas about complex numbers that are joined together, and I'm going to put them all in now, and then I'll move on to this stuff. So there's 3 ideas which go that a complex number originally invented to look something like this. It's this magical number I, and you have a real number plus a real number times I, and this produces a number with 2 parts. The word complex literally means made of more than one part. That's the literal meaning of the word complex. And so we have numbers that are made of 2 parts, so they're complex. This is called Cartesian form usually. In my head I call it rectangular form because you draw little rectangles. And so you locate A and B on an x and y axis, and this point is the point A plus BI. Yep. This is called an Argand diagram. So Argand was the mathematician who popularized the idea that complex numbers could be represented as part of a plane. On the other hand, there's a whole different way of describing where a complex number is, and it comes from polar form, they call it. Do we use cis? Where that's the radius, and then the angle measured anti-clockwise from the origin, from the x-axis is theta. Now I should say something. The number cis theta is literally a number all by itself. So this is actually the number, real number r times the complex number cis theta. It's not just a place to hold things. And different people in different places use different things. Over in electronics, they use J for what we use in maths for the number I, and they use r angle theta for their representation of this. There are lots of different representations. These are the ones in maths. And the useful thing is to be able to convert between these. And the main conversion that people use is via the picture here. That I can use Pythagoras' theorem from using the A and B to figure out what the R is. And I can use trigonometry to figure out what the theta is. And I can use trigonometry to figure out what the A and the B are from the R and the theta. So the usual way that we convert is that R cis theta is literally R times cos theta plus I sine theta. And that cis is short for cos I sine. Some mathematicians hate cis with a vengeance. Yep. I find it rather charming, actually. I think it's really cool that there is a function. This is a function that takes in a real number and spits out a complex number. I think that's kind of cool. And it's nice to know that those sorts of things exist. But just for future reference, there's an alternative way of writing this. Is e to the I theta. So if you look at places on the internet and you look up polar form of complex numbers, it will say this. So what de Moivre discovered was that cis behaves like powers behave. And so what Euler decided was that we would declare that actually it is a power of something. So let me talk about de Moivre's theorem now. I don't know how your lecturer defines de Moivre's theorem, but this is how I define it. Cis theta to the n is cis of n theta. Technically, I think it only applies if n is an integer. Okay? So that's how powers work. If you do powers of powers, you multiply the powers together. So look, we have function of theta and n to the power of n is the same as function of n times theta. That must mean that cis is a power of something, which it is. It's e to the I times theta. So that's where that came from. So that's de Moivre's theorem. I'm pretty sure. Does that seem right? Oh, well, that's not important. It is. So the thing is that now we can just use the properties of the way powers interact with multiplication. So we already know that for ordinary numbers, combined with, a times b to the n is a to the n times b to the n. That's always true for real numbers. We get r cis theta to the n is r to the n times cis theta to the n, which is r to the n times cis of n theta. That's the de Moivre's theorem you know and love. Okay, cool. But I don't remember this one, I just remember this one. Because there's no particular reason why the real number part should behave any differently to any other real number. You can do powers. So this one is the actual de Moivre's theorem in your notes. And so if your lecturer asks you what it is, you should probably write that down. But in my head, it's just this. I know what powers do to cis. Cool. So along with, this is de Moivre's theorem. No one seems to have, there's no named theorem that goes with how cis interacts with times and plus, but I should write them down. So these are the three rules for how cis interacts with times and divide and powers. Cis does not interact well with plus at all. There is no particular way of adding two numbers that are written as cis. I mean, you can literally draw the vectors and do vector addition, but the only way to deal with addition for complex numbers is to convert them back to Cartesian form. So when I think of de Moivre's theorem, it's in my head along with these two bits of information. Along with all these three bits of information here. And these are exactly the rules for how powers work. If you have e to the x divided by e to the y, it's the same as e to the x minus y. If you have e to the x times e to the y, e to the alpha times e to the beta, it'll be the same as e to the alpha plus beta. So these are the same rules for powers, which is why cis, and that's a useful way of thinking about it. Cis has the same rules for how powers interact with times and divide and other powers. Cool. So when people said de Moivre's theorem, they may have been thinking of a particular use that they wanted to talk about. Is that true? And if so, what were they thinking of? Yep. Real polynomials roots. Do we use de Moivre's theorem for that? Okay. Well, we can certainly use it for finding roots of things. So I'm just going to no, not that. Let's solve this equation. Z cubed is 1 plus I. Okay, great. So we know, based on what we just said there, that cis in particular interacts very well with powers. And so it would be much easier to solve this equation if it was in polar form. All right, let's convert to polar. Oh, can I change it to 1 minus I? No, just a second. Minus 1 plus I, please. Convert to polar. Okay, so here is my number. Minus 1 plus I is there. Over in this corner. I would need to convert to polar, I'm going to need to know how far from the centre it is, and I'm going to need to know what this angle here is. Okay. So the length of 1 plus I is the square root of 1 squared plus 1 squared. So that's these literal distances, 1 there, and then I do the square root of that in this little triangle, and that produces the answer I want. And so that is root 2. All right. And the angle, well, this angle in here, which I shall call alpha, tan of alpha is 1 over 1. And so the alpha must be pi on 4, like tan inverse of that. Which means that the theta must in fact be 3 pi on 4, because that whole thing is pi and then we have to go back pi on 4 to get to the angle I really want. Because this bit here is pi on 4 and that bit there is the rest of the pi from the pi on 4. Yep. Well, my alpha fits inside this triangle. So you could do that if you wanted. Yep.
The formula arctan B on A always true?
No. The formula arctan of B on A is not always true. That's why I chose this example. So I could have done this. I could have said that I could have done this. All right, I could have said that tan theta is the y coordinate, which is 1, divided by the x coordinate, which is -1. That's what you were thinking back there? Next to you? That's what you were thinking? You got the x coordinate? Yep, and that comes out to -1. Cool. And then you could go like, arctan of the -1 would be minus pi on 4. But that's not the right angle, because minus pi on 4 is down here. So I would have to look at my diagram and adjust that to give me the angle in the correct zone. And so therefore theta is in fact pi minus pi on 4, which is 3 pi on 4. So saying that the angle is tan inverse of B on A is actually wrong half the time. It's totally true to say that tan theta is B on A, that is always true. But it's not true to say tan inverse of B on A is theta. So if you want to do this, this is probably a decent way of writing the working. To say this is what arctan comes out to be, but because it's in this quadrant, it must be pi minus pi on 4. Yep. So basically, if it's on the right-hand side, where the real part is positive, then the theta will be arctan of B on A. If it's on the left-hand side, the theta will be pi plus arctan of B on A. Great. So 1 plus I is actually root 2 cis of 3 pi on 4. Beautiful. And so now what we're actually solving is z cubed is that. Cool, so I need to do the cube root of this, which is great. I could just divide it, do that. The traditional way of dealing with this is to say, well, just a second, that is not the only representation of this number. Cis of 3 pi and 4 will totally get me to this point, but so will all of these for any value of k that's a whole number. I need to do this because this cubic equation, being a cubic, should have 3 solutions. And if I'm going to do the cube root from here, I'm only going to get 1. So I'm setting up to get all the other solutions. Okay. So z will be that to the power of a third. That gets rid of the power of 3. And I'm using de Moivre's theorem now. So when this to that power is this to the third, and cis to the power of a third is a third times this. Because that's how de Moivre's theorem works. Technically, de Moivre's theorem only works for whole numbers, but we've adjusted it a little to allow us to use it for this. I may need to go back and do it more like the way your lecturer does it, but this is fine for the moment. So root 2 to the third is not going to be anything good. It's like the 6th root of 2. So I'm just going to do to the 6. Okay. So these are all of the solutions for z. But there's actually only 3. It looks like there's infinitely many, but every time this k becomes a multiple of 3, I end up adding 2 pi, and adding 2 pi to the angle doesn't change the position of the number, because it just means you go round a whole number, another 2 pi, and you end up back where you started. And so... 3 different solutions. Z is 2 to the 6 cis of pi on 4, and 2 to the 6 cis of pi on 4 plus 2 pi on 3, and 2 to the 6 cis of pi on 4 plus 4 pi on 3. Whatever those are. But when I get to 6 pi on 3, I'm back to plus 2 pi again, so I end up back at the beginning. So just to be sure that we've got this right, the 3 solutions should fill up the whole circle. So my original number was here. That's the original. And then my new solution was here at 1/3 of the angle it used to have. And then we go 2/3 of pi. I have no idea where that's going to end up. 3 pi. It's just about there. So that's where the numbers are. And our actual solutions are only at 2 to the power of a 6th away from the centre, so they're like here. Whoops, sorry, there. That's my 3 solutions there, those 3 green dots. This was my original number here. So I did the cube root, so that this number should get shorter, and the angle... I did 1/3 of the angle, but there's actually 2 other solutions.
So the power of the z indicates how many solutions there are?
Yep. So you've just asked the question, going to make sure that that's there. The power of z, this is z cubed, there should be 3 solutions. Z to the power of 4 should have 4 solutions, z to the power of 5 should have 5, z squared should have 2. And that's always true, and that's a polynomial thing. A polynomial of degree 3 should have 3 zeros. Yep. So this is how to solve one where it's just a straight up power equals number. And anything more complicated than that is more complicated than that. So, yeah. So that's the beginning of solving things like that. And that's why, I mean, if you actually want to go right back to it and do... I just want to show you something. It's pretty stupid. Now, I know the solutions to that. I know that the solutions to that are plus and minus I. All right, so just an aside. Z squared is minus 1 means that Z is plus or minus I. That's what I is for. That's what it's for. But I want to do it with polar form just so you can see what's going on. So I just want to do the whole thing. Convert minus 1 to polar. So I know this. I know what the answer is going to be. So I can convert minus 1 to polar. So minus 1 is here. So the length is 1. And the angle is pi. That's how you get to that. So we get that minus 1 is 1 cis of pi. Beautiful. So we get, which is the same as cis of pi plus multiples of 2 pi, right? Beautiful. And so we need to solve, I always put the L straight after the S, I don't know why. Which means the Z must be this to the half. which means it must be half of this, like that. And there's only going to be two solutions, because every time I get an even number, it'll be adding 2 pi. And so we get two solutions. Z is cis of pi on 2, and cis of pi on 2 plus pi. You ready? Pi on 2 is there. That's where I is. Plus another pi is there. That's where minus I is. So this is I and minus I. Just to really ram home of what's going on here. Right. Cool, huh? Well, I think it's cool. Yeah. Okay. Now, on the list was complex zeros of polynomials. The person who wrote that, what were you thinking?
Well, there was a question where I was just stuck because the example given on the board, I believe, was like equals to 1, where I wasn't sure how to get all the different roots of them with like the case.
So the thing that we just did then? So you had one that was like z to the 5 equals 1 or something in the lectures. Cool. So if it's equal... That's all right. That's all good. So if this was actually... If this was equal to plus 1, then this here would have been 0.
That one was easy. It was just with other numbers.
Yep. And so we've done one where it's something else horrible, like minus 1 plus I. And you're okay with that now? Okay. But I am going to look at complex numbers and polynomials anyway, because I think it's cool. So the thing is, the thing that complex numbers allow us to do is find zeros for all possible polynomials. For example, this doesn't have any zeros if x is real, because this number is always more than 0 if x is real. It's always more than 10 if x is real. Maybe not more than 10. If x was between minus 1 and... anyway, it's all good. If x was between minus 2 and 0, there would be some negative answers to this, but none of them are smaller than 10. So if you wanted to factorize this, you had to use complex numbers. And the quickest way of doing it is to use the quadratic formula. Okay, so you get x equals minus b plus or minus b squared minus 4 times a times c over 2a. Oh, look at that. I can pull that 4 out and it will be a 2. So this move here, they both had a 4, so I factorised it out and then I square rooted it and it got a 2. And that left me behind the 1 and the 10. That gave me a minus 9. The square root of 9 is 3 and the square root of the minus 1 is I. And so I got minus 1 plus or minus 3i. And so I can factorise this now by going that px, which was this, is now this. So it's x minus negative 1 plus 3i and x minus negative 1 minus 3i. So those are my solutions, negative 1 plus 3i and negative 1 minus 3i, and they both end up in this position here. And you always go x minus the solution. Square root of negative 1 times the square root of 9. Because square roots can go over times, so this is -1 times 9. So I can do the square root of the -1 and the square root of the 9. Yeah. And the square root of -1 is I. Oh, it's like that because we decided that it ought to work. So what we did when we added the number I to the real numbers is we would like a number such that I squared, a number such that that number squared is -1. So I squared is -1, which means the square root of -1 should be I. And we added it to the real numbers, specially making sure that all the rules of how real numbers behave and functions of real numbers behave still work. So we know that, just for that bit there, we know that for real numbers, square root of AB is the square root of A times square root of B. That works for real numbers, so we assume it works for imaginary numbers too. Yeah. That's why. So it has to work that way. If we want all of our rules for how real numbers behave to still be consistent and work for complex numbers too, then we have to allow this to happen. Okay. So here's the thing. There's a really useful piece of information, which is if you have a polynomial that has real coefficients, then if you have a complex number which does satisfy it, then its complex conjugate will be guaranteed to satisfy it as well. So that's a theorem. I don't know what it's called, but if polynomial Px has real coefficients and A plus Bi is a 0 of P, then A minus Bi is a 0 of P2 of P as well, like not P sub 2, P also. Okay, so we saw it here. We got -1 plus 3i, and we also got -1 minus 3i because our original polynomial had real coefficients. If the original polynomial has some coefficients that aren't real, I can't use this fact. It only works if the coefficients are real. And so what that means is that if you happen to think of one solution that works, then the conjugate has to work as well. And it also means that they can create these funky little problems where they give you an unknown polynomial and tell you one of its roots, and then you can figure out what its coefficients are. Okay, so here's a made-up example. The real polynomial Px is cubic, and P of 3 plus 2i is 0, and P of 0 is 5. Find Px. There will actually be several of them that do this, so I really hope I haven't painted myself into a corner and made it impossible to do this, but it should be enough. Okay. Have you guys heard the word monic in this course? Right, I'll add that. A real monic polynomial Px is cubic, and that, find Px. Okay, so let's see. Because it's cubic, well, not because it's cubic, because it's real, if 3 plus 2i is there, then 3 minus 2i will be there as well. So since is real, we know that 3 minus 2i is also 0. And that means that it must be divisible by x minus 3 plus 2i and x minus 3 minus 2i. So if something is 0, then you must be able to divide it by x minus that. So x squared minus 3 minus 2x minus 3 plus 2ix plus 3 plus 2i, 3 minus 2i. So I just expand the brackets there. The minus 2i and the plus 2i cancel. We get minus 6x. And that's a difference of 2 squares. So we get 3 squared minus 4i squared, but I squared is minus 1. So 3 squared plus 4 squared. So 3 plus squared is 9. 2 squared is so 13. Okay. I really should have included all that working. So to get this 6x, I notice that the minus 2i and the plus 2i will cancel each other out. And this one's going to give me 3 squared plus 2 minus 2i squared, because it's a difference of 2 squares. Not 9 squared, David. Rub it all out. 9 minus minus 4. So 2i squared is minus 4. That's the whole point of the I. Okay, it must be divisible by that. So it's monic. So the other coefficient, it must be like x minus something. For some real number, because it's cubic. So if it wasn't monic, then I need a coefficient out the front here as well. Monic means that the leading coefficient, the biggest power, has to have coefficient 1. So if it wasn't monic, I'd need like a times c or something as well. So we know that p of 0 is going to be 0 minus a, 0 squared minus 6 times 0 plus 13, which is minus 13a. And this is supposed to be 5. And so therefore a is minus 5/13. And so p of x is in fact x minus 5/13. X squared minus 6x plus 13, which is a perfectly good polynomial, and there is no point expanding it out. They just said, find the polynomial, I've found it, I can stop there. If they had said, find the coefficients of the polynomial, then I would have to expand it out. But that's a perfectly good cubic polynomial, so I can leave it like that. So that's not like a method that you're supposed to remember. It's just saying that you can use the information that you're given to fit together to find the polynomial you want. I used the fact that it was divisible by this to get an extra one and find a quadratic factor. I used the fact that this had to divide into it to say, well, there must be another factor. I used the fact that it was monic to say, well, I don't need a coefficient on that x. And then I used the fact that the p of 0 was 5 to find what this a is. But there would be lots of other ways of attacking this problem, just as much as this. Yep?
What other information would they have to give you if it wasn't a monic polynomial?
They would have had to give me probably the value of p at some other point. So a cubic has 4 coefficients. Has a constant x, x squared, x cubed. Cubic has 4 coefficients, so you need 4 bits of information to find it. I had 1, 2, 3, and the fact that it was real. 4. If it was just a monic, complex polynomial, then I don't have enough information. I need 4 bits of information to find a cubic. So if you only have 3 bits of information, then there will always be an unknown, and you'll be able to say, well, it's this, but A times this. Yeah. So yeah, that's a useful piece of thing. If something needs 4 bits of information to define it, then you need 4 bits of other information to find it. It's just like with trigonometry back at school. You need 3 pieces of information to tell you about a triangle. It doesn't have to be the 3 sides. It could be 2 of the angles and a side, and that would be enough. Yep. Cool. Well, probably time to stop, really. So I can eat before the Maths 1A revision seminar. But any other complex number sorts of questions before I run away, which I'm happy to answer?
I was going to just ask.
Yep.
Is the method any different for solving complex polynomials?
Is the method any different for solving complex polynomials?
Yeah.
No. Something like that. Well, I mean, so just give people a second to move. People, I'm still talking here, so can you do that quietly, please? I'm still talking here. So you're not asking this question, you're saying, what if this question didn't say it was real? What would I do then? Is that what you're asking?
No, it's just, if nothing changes when it changes to a complex number. I feel like if I saw a polynomial that had a bunch of, say it had 2 complex numbers in it and 2 real numbers in it, it would just confuse me, and I wouldn't know.
So you're looking at something like this one?
The fact that it is real, that information is really helpful, because the whole complex conjugate thing.
Yes, that's right.
It's easier, but yeah, when it's.
So,
If they just gave us, I don't know what it would look like. Kind of
yeah. Well, if you were just given bits of information about what its zeros were, you would literally just write them in, x minus thing, x minus thing, x minus thing. Yeah, and they might tell you, the monic might be useful in telling you the value at a certain spot, and you can figure out certain things. So, if I had something like, traditionally you put a z if it's got complex numbers in it. So I currently only have 3 bits of information. So I need another one, right? Something like that. So that would be enough information to find this polynomial. So, hopefully.
Yeah.
Not obvious. But we would need to have a complex number coefficient for each of them. We know what the leading coefficient is. 1, 2, 3. Yeah, well, let's give it a go. It says it was monic. So for this one, I might find it easier to just pick letters for them, because I don't know what's going on with the other one. So I'm going to do this instead. So these are going to be complex numbers. You know it's monic, so the one for x cubed is 1. I've just drawn it in the wrong direction, I'm sorry. And so we know that p of 2 plus I is 0, So alpha plus beta 2 plus I plus gamma 2 plus I squared plus 2 plus I cubed. Oh, that's bad. I don't like it. No, scrap. That's a bad plan. No, I want to know now, even though I just made it up.
So the alpha, beta, and the gamma represent complex numbers we don't know what they are.
Yep, that's right.
Does the real part, like, you know how polynomials always like possible, well they don't always, but yeah, is there always a real part? I don't know.
I don't know. Let's see what happens with this. It's definitely this. Because of that information, we definitely have this bit here. Because that's always true if it's out to 0. P of 0 would be beta, and that's supposed to be the number 2, according to that. Because this is 0 squared plus alpha times 0 plus beta. And that comes out to minus 2 plus I times beta, and it's supposed to be the answer 2. And so beta is 2 divided by minus 2 plus I, whatever that is. It's a perfectly good complex number all by itself. Yeah, well look at this. It's got 2 plus I on the bottom. If I multiply by 2 minus I down there, that'll make the bottom real. Right. Sweet. Doing so well. So we have one more coefficient to go. So let's just say, so to sum up, PZ is currently this. Okay. And P of 1 is 3 minus 5i. Let's go. All right, so this is minus 1 minus I here. And this is alpha plus 1/5 plus 2/5 of I, because 1 minus 4/5 is that. And this is supposed to be equal to 3 minus 5i. So I'll divide by the 1 minus I, and then add that. And that'll tell me what alpha is.
So is there some sort of rule, say you have an even number of complex numbers, that the end result will be a real polynomial? If it's, so say you have 4 complex numbers,
Yep.
would the end result always be real?
No. If you had 4 and they came in complex conjugate pairs, then yes. The whole point of the complex conjugate is that when you add a number to its complex conjugate, you get a real answer. And when you multiply a number by its complex conjugate, you also get a real answer. Which means that when you expand out x minus thing, all the coefficients end up being real. Yeah. So if I multiply both sides by 1 minus I, this is so not a question I would expect them to do in an exam. So that's 2. So we get 3 plus 5i minus 3i plus 5. Oh, look at that. And so therefore alpha is 4 minus a fifth, which is 19 fifths. There we go, we have it. Ta-da! And so P of z is z minus 2 plus I times z squared plus 19 fifths minus 7 fifths of I, z minus 4 fifths plus 2 fifths of I. No, they only asked me for a polynomial. I choose not to expand. So one of the cool things about this particular working here was that I didn't have to do any of the let the complex number be a plus bi. I could directly find it using complex number arithmetic. Over here, I didn't, I've got minus 2 plus I times b is 2. I could just divide, just in inverted commas, divide by this complex number to get an answer. And over here, when I had this equation to solve to figure out what alpha was, I could just divide by 2 and subtract, and it will do what it does. So you are allowed to use ordinary complex number arithmetic if you have something like this. But I would not expect something like this. At the very most, they could give you a quadratic maybe and say this is a complex quadratic, monic complex quadratic. It has this complex number root and this value when z is 0, and we would have solved it a couple of pages ago by then. Yeah.
So if it was quadratic, can you put a complex number into the quadratic formula?
Yes, you can, but then you need to know how to square root a complex number. Something like that. So if I wanted to solve that, I'll get z equals minus b plus or minus b squared minus 4ac. Oh, this one actually works quite nicely. So I do exactly what I normally do, and so then I get 4 times 3 is 12. So I get minus I plus or minus root 11 over 2, which is two perfectly good complex numbers. The problem would have happened if the I was here with the 3. Interestingly, these numbers are not complex conjugates. Because it's the real part that's been plus and minus, not the imaginary part.
Okay. Alright. Does the sign of the imaginary part change?
Nope.
No?
I just did that wrong.
Oh,
Yeah, the minus I stays the same. If I had had this, if I'd had that, then I would have had, well, not factorise, but solve. Then I could have done, minus b plus or minus b squared minus 4 times a times c over 2a. Then I need the square root of 1 minus 12i. And the only way I know to do a square root of a complex number is to write it in polar form.
do you provide the square root of the whole also? Yeah.
To find that, I need 1 minus 12i in polar form. And then you'd halve the angle and square root the length. Yeah. And then it would be really bizarre because I'm going to have minus 1 plus something in polar form, and so I'd probably have to turn the polar form back into Cartesian form for the thing to make sense at all. So these are a lot of very good what-if questions that help us to understand what's going on when we do these things, but I wouldn't expect most of them to be in an exam. Now you know, now you've seen them, you guys will be fine. Yeah. I don't know, 2 hours isn't that long. Which is why they don't ask really complicated questions in exams, because you just don't have time. But what that means is that for the lecturer, what's complicated is not always the same as what's complicated for you, because for them, they need to have, when they ask a question, they try very hard not, to account for the fact that you don't already know the answer. But when they're doing a related weights question, they're going to expect you to be able to go, these are the variables, here's the derivative, bang, there it is. So it's the same sort of thing. When you see something with polynomials like that, you're going to go, do you know what, the quickest way is to probably write it as x minus something. And make sure that's in there. So, yeah. Okay.